Okay, we're now moving into the part of Unit 1 of motion and forces, into the idea of forces. So let's move in first to talk about Newton's first law. So the key concepts, there's my kitty in the background. Newton's first law, here's what we're going to talk about today. What is a force? What is a net force? How is that different than any other force? And what happens when a net force is equal to 0? We're going to be looking at different forces and learning how to draw what we call free body diagrams. So today we're going to talk about what happens when you add up all the forces and the sum of the forces is 0. We say that's no net force, and we call that situation static equilibrium. Static meaning not moving, equilibrium meaning balanced. But we could also have what we call dynamic equilibrium. Dynamic, think of dynamic as something that is moving. But something that's moving but equilibrium means it's not accelerating. So, if we have no net force, then our object is not accelerating. But it could be moving at constant velocity, so constant speed and not changing direction. That would still be in equilibrium. We just call it dynamic equilibrium. So, what is a force? It's a push or a pull. It can cause motion, just as Aristotle understood. And it's an action that's going to create movement. Aristotle thought of the natural order of things, so Aristotle, like 300 BC or so, thought that the natural order thing was for things to be at rest. And it took a really long time for us to understand, no, the natural order is for things to be in motion. Galileo is who we credit for coming to that understanding. So, types of forces. First of all, force is a vector, much like acceleration and displacement and velocity. It has both magnitude, like how big a force, how much are you pushing or pulling, and then what is the direction. So, also a vector. Contact forces are forces that are two things that come in contact with each other. So a push or pull or a kick. Tension, if you tie a rope to something, you pull it. We say that's a contact force. Friction, when you have a block sliding on a ramp, that is going to have friction that's going to tend to slow it down. And finally, the normal force. The normal force, think of normal as in like perpendicular. So that is a force that acts when something is pushing on something perpendicular. So for example, if you have a table and then you have an apple sitting on a table, the weight of the apple is going to push the apple down, but the table is pushing back up on the apple, which is going to keep it from falling. And we call that force that pushes up, we call that the normal force. So the arrow up represents that normal force. We'll talk more about those in a second. But we also have field forces. So a few examples, gravity and electrostatic. We're going to talk about those in detail in the next couple units. We also will talk later on about the magnetic force, and we might get into a little bit talking about the strong and the weak nuclear forces. These are called action at a distance forces. They're not necessarily with two things touching each other, but one object has an effect on another object that is some distance removed. Okay. Let's look at equilibrium situations. If the sum of the forces is 0, that means we say we have no net force. If that's the case, we have constant velocity. We have no acceleration. And we say that a body is at rest, it will stay at rest. Or if a body is moving and there's no net force, it will keep on moving. Now, that is counter to our experience that if you roll something down a hallway and it's flat, it will eventually come to stop. But that's only because of friction. If friction isn't acting, then that ball would actually keep rolling forever. So we use a technique to understand forces by drawing what's called free body diagrams. In that free body diagram, we take some body and we separate it from all the objects around it, and we draw all the forces that are acting on it. So if we talk about this scenario where you have a block and it's sitting on a table and your rope is pulling on the block, but the block isn't actually moving. Well, that might be true if friction is kind of holding it there, if it's a heavy block. So let's look at all the forces that are acting on that block. What we're going to do is think about the fact that since the block is not moving, the sum of the forces must be equal to 0. So we say that the sum of the forces in the x direction is 0 and the sum of the forces in the y direction is 0. Therefore, the object doesn't move. So what forces do we have? Well, the first force we call the gravity force or the weight. Sometimes you'll see it written Fg, sometimes you'll see it written weight, sometimes you'll say the force of the weight. So we write at different times, but they all mean the same thing, the gravitational force. What is the weight of that thing pulling down? Okay? Next force, tension force. If we have a rope that's pulling, then we'll draw an arrow representing the tension force, so that'd be pulling to the right. We have friction that is acting opposite the tension force to keep that block from moving, and that would be towards the left. Now I tend to put the arrow at the lower corner to show that that's where the force is acting, where the block is touching the table. And then finally we have what's called the normal force. So the normal force is acting on the block. Now the block has weight, so it wants to fall. But there's a table there, so it can't fall. The table's pushing up on the block, keeping it from falling. That force pushing up on the block is called the normal force, or perpendicular force. So, some other free body diagrams. If you have a mass hanging from a string, then you would say, well, you've got a gravitational force pulling the mass down, and then you have a tension force pulling the mass up. If you have a block, and the block is sitting on the ramp, but the block is not sliding, you might say that there's a gravitational force pulling the block down. There's a normal force, because the normal force always acts perpendicular to the surface. So because that ramp is at this angle here, the perpendicular force is going to be perpendicular to that surface, or up towards the right, but at an angle. And finally, we have a friction force that is, again, parallel to the surface between the block and the ramp. So there are the three forces that are acting on this particular block. That is what we call the free body diagram. You isolate the body and draw all the forces on it. So here's an example problem. Let's work this one out. This would be a good thing to write down in your notes. An owner is pulling on her dog horizontally with a force of 70 newtons. Friction is acting on the opposite direction with 50 newtons. The dog has a mass of 15 kilograms. Draw the free body diagram of the dog. What is the net force? All right. First of all, here's my dog. Oftentimes you draw a picture of what's going on, and then you just isolate the dog to draw all of the forces acting on it. And so here's my picture of a dog. It's a block. Simple. So I indicate all the forces. I've got the force of the owner pulling at 70 newtons. I've got the friction acting the other direction of 50 newtons. I have the weight of the dog pushing down, and then the ground is pushing up. So the normal force is pushing up on the dog. The weight of the dog is pressing down. You could also call FW F sub G. In fact, I'm going to change it right now. And I'm going to make that F sub G so it's a little more consistent. So we're going to call that F sub G. In other words, the gravitational force. What is the net force on the dog? Well, 70 newtons to the right plus a negative 50 newtons to the left for a grand total of 20 newtons. Now that are all the forces. Those are all the forces in the X direction. What about the Y direction? Well, the dog isn't moving, which means that those two forces have to be balanced. Well, I should say it's not moving. It's not falling through the ground. So, given that, we know that the force in the Y direction has to be 0. So you'd say, oh, that doesn't look right. I got to fix that one too. We don't have normal and normal. We have gravitational. So we have a gravitational force. I did that wrong. Let's fix that again. We're going to have a normal force that's going up. Normal force going up, and gravitational force going down. That did not work. Gravitational force. Better. So therefore the normal force is equal to, when you solve that, you're going to get the normal force is equal to the gravitational force. Okay. Which of the following forces is a field force? Hopefully you recognize. It's not friction, it's not tension, it's not normal, it is magnetic. When all the forces of an object are combined or added, the net force is the total part that remains or does not cancel. So if you say that some of the forces in the X direction, what do we got? We got 30 newtons to the left, 20 newtons to the right. Add them up and we get negative 10 newtons. That would be the net force, the total force. Now Galileo was the one who recognized that the reason objects come to a stop is because of friction. Friction is actually a force that is slowing these things down. Without friction, you don't need a force to keep an object moving. It will just keep on going. So let's talk a little bit about friction. Friction is the name that we give to a force that acts between materials that touch. It's actually an electrostatic attraction repulsion that's going on, but friction is caused by the irregularities in the surface of the objects that are touching. So think like sandpaper. Sandpaper, two things of sandpaper is going to be a lot of friction. And then you think of something like something that's sort of greasy, is slippery, that's going to have low friction. So even very smooth surfaces have little irregularities that obstruct motion. So we often talk about if there's no friction, but there almost always is, at least a little bit. If friction were absent, a moving object would need no force whatever to remain in motion. Now Galileo came up with some thought experiments to help him understand how this could be true. And he thought about how the rolling balls behave on inclined planes. He thought a ball rolling down a plane is going to go faster. A ball rolling up is going to slow down. So he thought, well, what would a ball that's on a smooth, flat, horizontal surface do? It stands to reason, he thought, that if going down causes something to increase its speed, going up causes something to decrease its speed, then if it's no slope or flat, then the speed should not change. So in other words, if the ball is moving on a flat, it's going to keep going at that constant velocity. So again, if there were no friction, a ball would move on forever. He thought about another way, though. He thought about a ball that rolls down an inclined plane. He knows that once it rolls down, it's going to come down, but then it's going to come up to the same height it had before. And so if you take, after the decline, if you have the incline be a little less steep, the ball is still going to achieve the same height it had when it started. So he knew that. He'd observed that. So then his thought experiment is, well, what happens if I just keep making this more and more and more shallow? The ball is always going to come to the same height. But what if the ball gets infinitely shallow? In other words, what if it's flat? Then what does the ball do? And he speculated, then the ball is going to move forever. So that was sort of a secondary proof to this idea that a body in motion remains in motion unless acted upon by an outside force. Okay, the tendency to keep moving is the natural state, as opposed to what Aristotle thought. So the property of a body to resist changes to its state of motion is called inertia. So if some objects are harder to move than others, we like to quantify how hard they are to move, and we do it with the term inertia, also known as mass. So let's do another example problem. A book that weighs 12 newtons that rests on a table while a person is pushing down on it with a force of 4 newtons. Draw the Freebody diagram for the book and find the normal force of the table on the book. Okay, here we go. I set it up. I have my book. I have my normal force pushing up. I don't know how much that is. I have the weight of the book, which is 12 newtons pushing down. And so the total for normal force, well, let's do a sum of our forces and figure out what it is. Sum of the forces in the y direction is 0. I've got a normal force pushing down. Pushing up, which is why it's positive. I have the 4 Newton force that's pushing down, and I have a 12 Newton force pushing down. For a total of, if I solve for Fn, I'm going to get 16 newtons. So the sum of the forces is 16 newtons. The normal force pushing up has to equal the 2 other forces pushing down. Okay, another problem, example. A block that weighs 40 newton at rest in a frictionless and inclined ramp is held in place by a rope. So let's figure out the free body diagram for this one. First of all, I draw a little picture of what's going on. Here is my book, and here is my rope. Now I want the free body diagram. Make it a little bit bigger. I've got the book, I've got the tension of the rope pulling up, and I've got the weight pulling down. I've also got, whoops, let's go back. I've also got, which I didn't seem to write here, the normal force pushing up. So I've got all 3. Okay. Back to inertia. Mass is the quantity that we use to measure inertia. So the more mass something has, the harder it is to get it to move. The law of inertia, which is now also known as Newton's first law, which, by the way, Galileo came up with this law. It's just that Newton kind of took it over when he came up with all 3 of his laws. The law of inertia, which is Galileo's first law, says a body in motion remains in motion unless acted upon by an outside net force. Mass is the fundamental quantity that we can measure to see how that works. All right, a couple little cartoons. A body at rest tends to stay at rest. The doggy thinks of a cat, takes off, and the person stays right where they are. And then a body in motion tends to stay in motion. There you go. Okay, mass and weight. In our language, we talk about them synonymously, but they're not the same. When you guys have been using the scales in the classroom, you've been measuring mass, which is in kilograms. When you measure weight, that is a product of your mass times the acceleration of gravity. That is your weight, or the force of gravity. Okay? So when you step on a scale at home, it's actually telling you your weight, but it's telling you your weight in pounds. And that is a weight, but it's not telling you your mass. Mass, the equivalent of pounds, is slugs. And who wants to know how many slugs they weigh? Mass is not going to vary no matter where you are. So your mass is the same on Earth as it is on the Moon, as it is in Mars, as it is flying through space. But your weight, because your weight is a product of your mass and the gravity acceleration of where you are, that is going to vary. Because here on Earth, gravity is 9.8. Up on the Moon, it's 1/6 that. Out on Mars, I don't know what it is, but it's not g. So your weight will vary, your mass never will. Units for newtons. Newton, by the way, is the unit we use, the SI unit for force. And since it is m times g, we know it's going to be kilograms. And the gravity acceleration is meters per second squared. So that is how we know what our unit for force is. And there it is. Okay? Which is also known as a newton. By the way, 1 newton, if you want to know about how much a newton weighs, it's about the weight of 1 apple. So just think about the weight of an apple, like Newton had the apple fall. That's about how much 1 newton is. So mass is a quantity of matter in an object. It is a measure of the inertia, or how hard it is to get it to move. Weight is the force of gravity on an object. So F equals mg. Notice that force and gravity, acceleration, is a vector. Gravity is down, and it has a value 9.8 here on Earth. SI unit, kilogram meters per second squared. Okay, a couple last concept questions, and we're done. Galileo showed that if friction were not present, what would be true? Moving objects would slow down anyway. Balls rolling on a flat plane would slow down on their own. Balls moving horizontally would move forever. The correct answer is C. If friction were not present, balls would move forever. Law of inertia states that an object at rest will remain at rest unless acted upon by an outside force. Yes. Will continue moving at the same velocity unless an outside force acts on it. Yes. Will continue moving in straight line unless an outside force acts on it. Also yes. All of the above. The law of inertia applies to moving objects, objects that are not moving, both moving and non-moving objects. Of course, the answer to that is C. Law of inertia applies to anything, if it's moving or not moving. Body in motion remains in motion. Body at rest remains at rest. A block is being pulled at a constant velocity by a horizontal rope of tension 5 newtons. The net force on the block is, well, you might think 5 newtons because that's the only force they tell you about, but it tells you that it's moving at constant velocity. So that is the dead giveaway. If it's moving at constant velocity, it's in dynamic equilibrium, which means the sum of the forces has to be 0, which means this block you're pulling with a 5 newton tension must have friction acting in the opposite direction, since it's moving at constant velocity. The sum of the forces is 0. So the answer is C. And that concludes our lesson for today.